Hello, welcome back. This is now section 7.3. We're going to deal with another method called the shell method. And you could do the same kind of problems with this method, but sometimes it's hard. If you remember, a lot of times we have to solve for the other variable in the equation. Sometimes it's not possible for whatever reason. Maybe you just don't remember how to. You got to complete the square to get it done or whatever. But sometimes it's useful to have this other method in your back pocket in order to pull off problems. Okay, so this is the shell method, and in particular now the rectangles are going to be parallel to the axis of rotation. So I always think of the kind of the rhyming scheme: shell equals parallel. Okay, so let's take a look at kind of the theory. What are the objects that the Riemann person now is adding up? Let's do the kind of flagpole orientation. Here's my Riemann person, and that person is going to go up the flagpole. And the sort of variable to which that you're describing the rectangles now, that's the same deal. So the base of the rectangle tells you what variable you're going to be in. In this case, the location of the rectangle is going to be at some position y sub I, and then the curve, we'll just give it some generic name like g of y. Okay. All right, so what exactly is the shell? The shell is the result of rotating that object parallel to some axis. So in this case, to get the parallel phenomena, we'll rotate it and unlike what we did with the disk, where we would rotate it around maybe the y-axis, here now we take that rectangle and rotate it around the x-axis. And the result is kind of like this. If you've ever seen the Flintstones and they have those cars in the Flintstones, the result of that red rectangle is going to be one of those things. It's basically a cylinder that's been hollowed out. And quite frankly, it is a washer, okay? But its height is going to be longer, right? Cheat a little bit with the perspective, and okay, that's where it would be opening in the back, but you can't really see it, right? Right, so there it is in 3 dimensions. Let me try to put in my axes. And so the original rectangle that was rotated, where is that? That would be sitting right here. Okay, so what's going to happen then is you are going, the resulting picture is going to be like a bunch of like a Christmas, no, like a wedding cake more phenomena. The Riemann man is going to be, collecting this this shell, and then there's going to be a nested shell inside of it, and that will be another volume that they'll collect. And then there'll be another shell inside of that, and then they'll collect that volume, etc. Okay, all the way to the top, and then you'll kind of see that popping out there. I make this a little bit more 3-dimensional. Okay, so that's just 1, 2, 3, 4 shells, and then you take the limit as the number of shells goes to infinity, and the end result is an approximation of this kind of hemisphere type object, and maybe kind of like this. Okay, that's this picture. If you take the limit as the number of shells goes to it, you get that. Okay, so we need a formula for the volume of the shell thing here, just like we did before with the big radius, and for washer we had little radius. Now it's going to be a little different. We'll have a radius function again, but then we'll have a different function for height. Okay, so the book does an okay job of presenting this. There's a more intuitive way that you'll see in other books, like the Stewart book. If you look around at different books, what you're going to do is cut this shell and then just lay it out flat, right? So I cut it along that blue dashed line, and then I'm going to unravel it and lay it out flat. And then it becomes a rectangular solid, And I could figure out the volume of that just by doing length times width times height or whatever. Okay. So there it is laid out. The original rectangle is inside of it somewhere. And we can then easily get the volume, because we know the volume of a rectangular solid, or like an elongated cube is basically what a rectangular solid is. So I need to get the dimensions, right? So the first dimension that I'm going to get after is this length here. And if you look at the red rectangle, that's just the length of the red rectangle. So for any given position y sub I, that length will be g of y sub I. The second dimension I'll get is this sort of length here, and that's just the width of the rectangle. So in our case, that width is change in y, right there. Okay, so change in y over here. And then finally you need this distance. Okay? And we think about geometry and what is that? Well, before we unraveled it, it was basically the circumference of a circle. So we're going to cheat a little bit and just say, okay, this is basically more or less, if you had a really, really thin shell, you could approximate it with the circumference of a circle, right? So it's going to be 2 pi r. In our case, the radius then is just the y position, right? So the radius of that cylinder there, that cylinder thing in yellow, is just the distance from the center to the outer portion. And if you look at the original picture, where is that? Well, that's just given by y sub I, right? It's the position of your particular rectangle. So we'll say then it's just y sub I. Sorry, I put it in a different color. But ultimately then just multiply the 3 together, you get 2 pi y sub I times g of y sub I times delta y. Okay? And there you go. Then you just have your Riemann person, sum all those up, and then we take the limit of it, and you end up with another integral. This time it'll have, instead of just pi r squared, it'll have a 2 pi in front, and then we have this y, and then the function g of y, and then delta y. Okay. In more general terms, then, this y thing is going to be a radius function. And for whatever reasons, the book used the letter rho, the Greek letter rho, which kind of looks like a P. And then this other guy here, they're going to call that the height function, which is basically the height of the rectangle. Okay, and they're always going to use h of y. Okay. But that pretty much does it. Let me rewrite the integral in the general form then. So in general, you'll have 2 pi from c to the d of the radius function times the height function dy. Or if it's in the other orientation, it'll be rho of x, h of x dx. Okay. Okay, so now we want to maybe look at the exercises over here in the book and kind of see what's going on, right? So let's try maybe number 7. Looks like it's reasonable. So we have y equals 1/4 x squared, y equals 0, and then x equals 4. Okay, that first guy is just a parabola with vertex at 0, 0. At 1, 2, 3, 4. At 2, it's going to give an output of 1. And then at, let's get another nice number, 4, it's going to give an output of 4. Right, so 4 squared is 16 divided by 4. So there's a picture of it in the first quadrant there. Usually it's just the first quadrant we deal with. And then y equals 0 is going to be the x-axis. Sorry, just 1 second. I'm noting something down. Sorry. Okay, so the x-axis is right there, and then x equals 4 is right here. So the region we're rotating is this region. And then which axis are we going about? I have to read up here. It's the y-axis. Okay. So first thing to note, this method is more powerful than the disk because it eliminates the shell issue. This object that you would be spinning around would have kind of a hole in it you could push down into, and it's like a bucket with the middles, with the innards scooped out a bit. But it has a hole in it, and so if you use the previous chapter information, you'd have to do a washer here. But with the shell method, you need not worry about that. Okay, so anyways, the rectangles are parallel. Shell is parallel to the axis of rotation. The base of that rectangle is on the x-axis, so then you know your formulas for the radius and the height. They're both in terms of x. Okay, so we have rho of x and then h of x. And so I need to get those items taken care of. So the radius function is just the distance from the center of the particular shell to the rectangle. Okay, so if you rotated that red rectangle, it would result in an object like this. So what we're looking for is the distance from here to here, which for any particular x sub I, that's just going to be x sub I. The distance from the center to the rectangle is just given by x. So this turns out to be true in general. If you have an x-axis or a y-axis rotation, the radius function will just be x, or the radius function will just be y. Okay, if it's a shifted axis, then you have to do kind of one of those differences. Anyways, the height function then is given by the actual curve itself. That will just be 1/4 x squared. And then we could dump it into the integral. Our Riemann person is going in this direction this time, collecting all of those volumes. So I'm going to go from 0 to 4, and then it's 1/4 x squared times x dx. And from there, it's just, computation. So factor out the constant. X squared times x is x cubed. So I get pi over 8 x to the 4th. And then that will be pi over 8 x. So plugging in 4, it'll be 4 to the 4th. So I think it's 32. When all is said and done, let me compute that using my Calculatron. 5,000 divided by 8. Yeah, 32 pi. Drum roll. And of course I screwed it up. So, oh, that was number 5, sorry. Yep, got it, sweet. All right, so that's the shell in a nutshell, so to speak. Let's look at sort of kind of there's this annoying issue that you see come up in number 15 and also present itself in the homework. And it really illustrates the fact that sometimes you do not want to do the shell method. You just want to stick with the disk method. And this is a common theme through Calc 2 and Calc 3 with integration. Sometimes you'll have 2 different ways to integrate something, and one way is obnoxious and the other way is easy. And you have to kind of figure it out, which way is going to be the quickest. And then ultimately, if you're a programmer, program your computer to figure that out as well. So anyways, number 15, let's take a look-see. I got y equals 1 over x, and I want to do a rotation, this time about the x-axis. And you see there's an issue there with the little rectangles. Okay, so I'm going to be rotating from 1 to 2. At 1, it's just going to go up to 1. At 2, it's going to go up to 1/2, and then it's going to die down like this. And that's the region we are rotating. Okay, so you see in the picture on the right, there is an issue. They have this kind of frontier line right here, this purple line I'm drawing. Why do they do that? Okay, let's get sort of a fundamental rectangle in this first region, just plop it down there. In that first region, that rectangle does not change. It's constant, right? And then once you get above that that purple line, then all of a sudden it's a variable rectangle. So up in that second region, it becomes variable. your variable of integration, because of the base of the rectangle is on the y-axis, you're going to be integrating with respect to y. So you're going to need some formula, rho of y, h of y. Okay. But anyways, the Riemann person is running up the flagpole this time, collecting those. We're rotating about the x-axis, by the way. Shells are parallel to the axis of rotation. And okay, so in that first region, what I'm saying is that the rectangle, the shell that's being produced by this rectangle, it's a constant value with regards to rho and h. I mean, and rho is variable, right? Rho is the radius from the center, which is going to be the x-axis, to that rectangle. That's just given by the value y. It's the height that I should be saying. That is the height value is not variable. So the height of that rectangle, no matter what y value you pick underneath that purple dashed line, it is going to be the same. It's always 1. It's always just the length from 1 to 2. That's just 1. Okay, but that only occurs from y equals 0 to whatever the heck this point is, this value. And of course we could figure that out. That point is 2 comma 1/2 using the function. So and from 0 to 1/2, yeah, that's true. Okay, the problem is now there's another interval with a different rectangle. So from 1/2 to 1, well, the radius function is the same. The distance to the rectangle is just going to be given by y, but the height function is variable now. Okay, so what is going to be the height? And what I'm saying is you could kind of figure it out. You're going to have to do, well, there's kind of that little gap there. So it's a difference, okay, long story short. All right, so the purple rectangle is going to be the difference between the distance to the top of it minus the distance to the bottom of it. Okay. So it's going to be the distance to the top given by the function itself. So we just find the inverse of that function. It's just going to be x equals 1 over y. Multiply both sides by x, divide both sides by y. So over on the right in this interval, it'll be 1 over y. And then you have to subtract away the distance to the bottom of the rectangle. Okay, so the distance to the bottom of the rectangle is constant. It's just 1. Okay, so there it is. And to compute this, you have to do 2 integrals, which is kind of an annoyance, right? It's going to be 2 pi times the integral from 0 to 1/2 of y times 1 dy, and then plus 2 pi times the integral from 1/2 to 1 of y times 1 over y minus 1 dy. Okay. All right, so evaluating these things, what do we get? So it's 2 pi times y squared over 2 is just going to be pi times y squared. Evaluate from 0 to 1/2. Plus 2 pi, if I distribute over here, the resulting function is going to be 1 minus y. So I have integrating that, y minus y squared over 2. And then I need to evaluate that from 1/2 to 1. Okay. And so evaluating the antiderivative at the limits, I get pi times 1/4 squared minus pi times 0. So pi times 1/2 squared is 1/4. And then plus 2 pi times, plugging in 1, I get 1 minus 1/2. And then minus, plugging in 1/2, I get 1/2 minus 1/4 divided by 2, which is 1/8. Okay. So now it's pi over 4 plus 2 pi times these 1/2 minus 1/2 is 1. 1 minus 1 is 0. Distribute the negative, so you get 1/8 there. That will be pi over 4 plus pi over 4, which is 2 pi over 4, which is pi over 2. Okay, drum roll. Yay. All right, so the spiel here is that this method is considered to not be great. All right, the troublemaker is that in the first realm there, the top curve and the bottom curve are different than what's going on in the second realm. Right, the top curve then becomes variable There, in our case, the curve to the right becomes variable, where the bottom curve is the same. So you needed two integrals. Okay, but it would have been one heck of a lot easier if you would have just done your disk method, right? So please note, using your brain is an important thing. It's not just, in my opinion, enough for you to use your brain to figure this out. It would be this is something you'd want to program into your computer to artificial intelligence. Think about it. You know, which method is the most ideal so you can minimize time and costs. You got to figure out how to figure that out. But anyways, if you use the disk method, the disk rectangles are always perpendicular to the axis of rotation. Then you could, you just plain old use the regular function. You would have an r of x. There's no hole in this object, so it's just going to be 1 over x. And then you go pi r squared, so 1 over x squared dx, and you're integrating from 1 to 2. A lot easier, in my opinion. So that's pi 1 over x squared is the same as x to the negative 2. So I get the integral of x to the negative 2 dx. And then that will be pi, add 1 to the old exponent, divide by negative 1. So that would be negative pi all over x from 1 to 2. So that's going to be equal to negative pi over 2 minus negative pi over 1, which is just going to be negative pi over 2 plus pi, which of course is what we got before, but now with a lot less work. Okay, so the bullet point of this PowerPoint is that you need to think. You need to start thinking about what is the optimal strategy, okay, before you even go in. It's just chess players, if you ask them about playing chess, they're always like, any strategy is better than no strategy. Okay? So anything is better than nothing, and hopefully that kind of sinks into your brain. All right, so there, great, good stuff. Okay, we want to start worrying about non-axis rotations. Then these, are a little bit more complicated because that radius function needs to be adjusted. Okay, so non-axis, and I'll just say the radius function, whether it be p rho of y, it will not be equal to y here. And then if it's rho of x, it will not be just equal to x. If it's axis rotations, those will be true. They would actually equal y and so forth. So anyways, let's find one of these characters where we have a non-axis rotation. Basically, try number 23. And okay, so y equals 2x minus x squared, and then y equals 0, and I want to go about the line x equals 4. All right, so this guy, one of our parabolas, the vertex, I always like to get the vertex of negative b, or sorry, just b all over 2a, or is it negative b? So negative b, so negative 2 all over 2 times negative 1 is going to be positive 1. And then the y coordinate plugging back in is 2 minus 1, which is 1. You can also find it by doing the derivative, right? So 2 minus 2x, so 2x is equal to 2, x is equal to 1. But anyways, there's our vertex, and then you could get, the y-intercept is just 0, so that hopefully will be enough to kind of graph it and get an idea. So I got 0, 0, and then what did he say? 1, 1. It's a sad face parabola because the leading coefficient is negative. So it'll go down like this. It'll probably go through 2. Y equals 0, of course, is your x-axis. And then we want to rotate 1, 2, 3, 4 about the line x equals 4. So you get kind of the half of a bagel or something like that, rotating like that. Again, the rectangle for shells is parallel to the axis of rotation. So our particular shell in this case would kind of look like this. Oops, maybe a little too, so I butchered that, but there it is. this guy, right? So we need the radius function, which will be the distance from the axis of rotation over to the outer part of the shell, or to the position of the rectangle that generated the shell. And then we also need the height function, which is this distance. Okay, so this is our h of, in this case, x. The base of the rectangle is on the x-axis. This is your rho of x. Okie dokie. So, right, I need formulas for these things. The height function, to me, seems the lowest hanging fruit. That's just going to be designated for any value of x sub I where your rectangle is located. The height is just going to be 2x minus x squared, right? So it's just 2x minus x squared. The radius function is a little bit weird, right? So what I'm looking for is a function that tells me this distance for any given particular x. So how do I get that distance? Well, you can think in terms of differences, right? So I can take a difference between this blue distance, which is just x, and then subtract away, sorry, that blue distance is 4, and then subtract away the distance to the rectangle, which is just x, right? So this distance to the axis minus this distance to the rectangle gives you the distance to the rectangle from the axis, right? So subtract minus x, and that turns out to flip the bill. And that's generally how it works. You know, I haven't really programmed it out for a computer or anything, but that maybe next year, right? Okay. All right, so after that point, you can dump it all into your integral du jour, and then send your Riemann man across and take the limit, you know, whatever, Riemann person. So it's the integral. We always got a 2 pi for these cases. It's going from 0 to 2. And you got 4 minus x times 2x minus x squared, and then all that dx'd. So a little bit of annoyance with foiling. Okay, so great. A little bit of arithmetic. Let's make this the video quiz. You go ahead and evaluate that. I'll even kind of show you the answer. Where is it? It's going to be, where? No, that's not. Is that it? It's 8 pi. Okay, yeah, so the answer is 8 pi. So that will be the video quiz. Hopefully you'll get that. Okay, so great. Let's look at, see if there's any kind of challenge problems in the homework, challenging problems. Number 9, for some reason, number 9 is quite annoying. Just for the sake that it's a bit unusual because the region that's being designated is underneath the axis, where as usual, the usual case is that it will be in the first quadrant. Okay, so how does that affect things going in? This is number 9. All right, so great. So the curve is y equals 6 minus x, and then 2, 3, 4, 5, 6, and 2, 3. So down 1 over 1, down 1 over 1, down 1 over 1. So it's this curve, and we want to go from 6 to 9. And we're rotating it about the x-axis, okay? And we're using shells, so the rectangle is going to be parallel. And the deal is here, I believe, with this guy, you can flip that region above the x-axis and then rotate it and get the same thing, but you're going to have to change the formula. Okay, so if you're not going to change the formula, then you need to worry about what your radius function is. Let me get my Riemann person situated. So the base of the rectangle is going to be projected onto the y-axis. So I know my formulas need to be, and I always like to do rho first, rho of y, h of y. Okay, great. So the radius function is what's going to change. The height function, of course, we're going to need to put everything in terms of y. So let's do that. So add the x over, subtract the y over, and 6 minus y is going to give the location of the bottom of the rectangle for a particular y sub I. We want to know the length of that rectangle though, so it's going to be a difference. It's the distance to the top of the rectangle minus the distance to the bottom of the rectangle. So I guess in this case it's going to be 9 minus the distance to the bottom is just that 6 minus y. Okay. Then the radius function is where it gets a little weird, right? So the actual distance to that particular rectangle, sure, is y sub I, but for our radius, we need it to be a positive radius. And right now, if you were to input that into your function, it would be negative, and we would end up with a negative area. It's probably what you would have done if you were left to your own devices. So what you really need to do is write it as negative y. That will cause the radius output to be positive, and things will work as normal. Okay, so ultimately then our integral 2 pi times negative y times 9 minus 6, of course, is 3, and then negative plus y dy, and the Riemann person is running from -3 to 0. Okay, so this will be 2 pi integral -3y minus y squared dy, rolling right along, equals 2 pi times -3y squared over 2 minus y cubed over 3, evaluated from -3 to 0, is 2 pi, and then if you plug in 0, you'll get 0 minus plugging in -3 will be -27 halves, then minus plus 27 thirds, and then 2 pi, this will be minus, so it's going to be 27 halves minus 27 thirds. So multiplying top and bottom here by 3, multiply top and bottom here by 2, and you should get 3 27ths minus 2 27ths is going to be 1 27th, and then all over 6, and then 2 over 6 is the same as 1 over 3, and then 27 divided by 3 is 9. Okay, great. So hopefully that, what the heck is this? Is this a difficult problem? I don't think so. Oh, the torus problem. So number 8, let me just go through this one. I doubt I'll have time to do it in class, so I'll go through it for you. Obviously, you probably may want to try it on your own, but this one is a bit tricky with regards to the integration. So they do give you some hints in order to evaluate the integral. Okie dokie. So how does this work? Let's set up the picture. So I have some circle I want rotated about some line. In this case, we position the line at 8, and I guess the circle has radius 7. So first go after the formula. Okay, so it's shells. Shells are parallel. There's my rectangle. The base of it is with respect to x, and we're rotating about that line, x equals 8. Okay, so when you do the rotation, what it is, it's a big donut, but in mathematics, for whatever reason, we call it a torus. Okay, I'm not an expert on toruses by any means. Go watch YouTube. Okay, all right. So anyways, rotating that thing, I will get my particular shell, and then I need to send my Riemann person across the x-axis, collecting those shells, and right. Okay. So I need a function to describe the height of that rectangle, and so the function that just plainly describes that circle is this. It's not a function, but implicitly it's x squared plus y squared is 49. Okay. And then we're going to solve for y to get our function. And of course, y is plus or minus square root 49 minus x squared. I'll just work with the positive portion, which is the upper hemisphere of the circle. Okay, it's this blue portion. Okay, great. So for the height function, at least, h of x, I can figure out the half of the rectangle's length given any particular x value position, maybe right here. Half that rectangle is going to be designated by that function y equals square root 49 minus x squared. So to get the full rectangle, you just multiply by 2 because of symmetry, right? So it'd be this. And then the radius function, it might be a little bit of trouble. It's one of these shifted axes. So you know it's going to be like 8 minus x. But let's just make sure. So in general, it'll be x, you know, the axis of rotation minus the input variable. Okay. So 8 minus x, let's just make sure, what am I after? I'm after the distance from the axis of rotation to the rectangle. And then what is that? Well, that's the difference, right? That's the difference between this rectangle and this smaller rectangle. So the big rectangle is given by 8. The smaller rectangle is the x position. So yeah, it's definitely going to be 8 minus x. So the setup is no big deal. Okay, it's the integration which is the troublemaker. And so let's go to our shell formula, 2 pi integral from, and you can't cut this one because the volume on the outer portion of the bagel or the donut is going to be more than the inner portion. So you can't say by symmetry, I'm just going to integrate from 0 to 7. That's not going to work, folks. You're going to have to go from -7 to 7. And then it's going to be, let's put the radius function first. 8 minus x times 2 square root of 49 minus x squared, okay, dx, right here. Okay, I'm going to distribute this item to these two parts. Otherwise, I'm not really going to make a lot of headway. You try a u sub and hope for some cancellation, but it ain't going to pan out. Okay, you're not going to get this binomial to somehow cancel. So it turns out the only approach really is to first distribute. So I'll have 16 square root 49 minus x squared, and I'm going to split it up into 2 integrals, and then minus 2 pi times the integral of, I guess we have a 2x, and then square root 49 minus x squared dx. And we're going from -7 to 7. Okay, so the first integral maybe is still a bit of a mystery. We can factor out the constant. Let's clean it up a little bit then. So we get 32 pi integral from -7 to 7 of the square root of 49 minus x squared dx. And then the second integral minus 4 pi integral x square root 49 minus x squared dx, going from -7 to 7. Okay. That first integral is kind of, you're not going to learn how to do that just for a while, okay? But it turns out there's a geometric shortcut that you can use, and that's the hint they give you in the problem. Basically, what that represents is the area underneath that semicircle going from -7 to 7. That's this area right here, and we know the formula for the area of a circle. The area of a circle is pi r squared. So the area of half that circle, the semicircle, is going to be 1/2 pi r squared. Okay, so if you know the radius, you can figure out that blue integral, that blue boxed integral. So 32, we know the radius is 7, so it's going to be 1/2 times pi times 7 squared, which is 49. Okay, so that guy's done. The second integral may not be obvious to you, but to me, the function is odd. Okay, this function is an odd function. And when you're integrating over a region of an odd function, so this guy probably looks something like this, this region will be negative and this region will be positive, and the areas will then cancel out when you add them up. Okay, so long story short, this guy is just going to be 0. And you can verify that by actually doing a u sub for the radical portion, and you'll find out that you get 0 when all is said and done. Okay, so that whole integral is going to be 0. 4 pi times 0 is just 0. So you end up with this expression here. 32 times 1/2 is 16. 16 times 49. Is 784. and then that's it. You know, you got your answer. Okay, so. Right. So those are some of the you know the evenness and using geometry. That's not going to come up a lot. So oftentimes you'll forget it. In Calculus 1, we kind of touch on it when we're talking about integrals, but okay. So there's that. Hopefully, okay. So thank you for watching, and I will see you next time.